problems 13 and 14 on worksheet 7. So these problems are a little bit harder than anything that we will be asking you to do on the test, but they're really important for understanding what's happening in these problems. So in 13, we have the absolute value of this is equal to some kind of number, right? So we have the absolute value of a quadratic is equal to some kind of number. So we have to factor these things in order to figure out what the answers are. So we break them into two cases, and we end up with 4 separate things that we can plug into the original that ends up giving us either 3 or -3 on the inside of the absolute value, which would then be equal to 3, right? So we have this situation. Algebraically, we can solve it by breaking it into two cases, just like normal, and then setting them equal to 0 and factoring like any quadratic problem that we have. So what's actually happening? When we look at the graph, we're taking y equals each side of the equation, okay? So if I'm saying that absolute value of x squared plus x minus 9 is equal to 3, I'm taking this red graph and I'm saying that the absolute value of this parabola, which is kind of a goofy looking W thing, and then I'm taking 3, which is this blue horizontal line. And what I'm trying to do is, if I have the absolute value of x squared plus x minus 9 equals 3, what I'm trying to do is I'm trying to say, okay, since I've replaced each of these with y values on my graph, what I want to do is I want to, I shouldn't have put a y here, I should have put a 3 here. But what I'm trying to do is I'm trying to figure out where are they equal, right? So they're going to be equal when y equals 3, clearly, but this has to have the exact same value as this one. So when both of these y's are 3, then these things are equal. So what does that represent? That represents when I look at x values that make that work, because in the problem that I have, there are no y values. So what I'm doing is when my y values are the same, then my answer works. And so I have to look at, in the problem, x values that make that work. So look, there are 4 times that just so happen to match perfectly with the 4 times that we solve algebraically that this thing works out. So that's kind of what's going on. The graph just is another way to represent this equation. Graphs and equations always have some sort of, like, they're perfectly aligned. We don't have these things just to have them. Now, number 14, algebraically, we have to break the first part into 2 cases. So we isolated the x plus 4 absolute value. And then after that, we have to isolate the second absolute value and break that into 2 cases. So we end up with 4 things going on. One of these doesn't make any sense. This is always true. And since this is always true, and this is always true, and this is an and problem, then we stick with this. Since this is never true and it's an and problem, none of this works. So we end up with -3 to infinity. Like, algebraically, that's what makes sense. But if we look at the graph, it also makes sense. We're trying to figure out where absolute value of x plus 4 is greater than or equal to absolute value of x minus 2. And that happens when this red graph is higher than the blue graph. So notice they intersect at x equals -3. And then the red graph is higher from then on. It has greater y values than the blue graph, which means that this value is going to be greater than or equal to this value every time after this intersection, which would be -3 to infinity.